Alright guys, so what I wanted to do is just kind of make a couple videos that hopefully will help you to study and remind you of some of the main topics that we talked about. Big thing I want to mention is that this topic list is not exhaustive. So I listed some of the major things that we talked about. I'm not going to talk about all of these things, but and again, this is not exhaustive. So you need to go back and look at your worksheets, look at your tests. Make sure that you understand and are clear on how to do each problem from each test. But I will talk about some of the main topics in this video. So let's just go through real quick. Looking at test 1, a lot of this should be review from Algebra 2. So we really just wanted to reinforce a lot of the concepts from Algebra 2 that you should have picked up on. There are some new ones in there, sum and product of roots we didn't talk about, and we do have a proof for that. Quadratic formula proof you did in Algebra 2, but we did again in this class, and then building quadratics was a new topic. So that's all from test 1. Test 2 is really where we got into matrices and how to use matrices in different settings. So number 1 was finding the equation of a line using determinant method. We looked at a lot of different matrix operations, addition, subtraction, multiplication, inverses, all of those things. Augmented matrices, so using row operations in order to solve augmented matrices. Proving matrices are inverses of one another. Kramer's rule and the proof. And then consistent dependent matrices where you had to introduce a parameter in order to come up with the solution. Test 3, more matrix algebra, building a quadratic using matrix algebra, given 3 points. Logarithms and exponential functions was the main topic on here. So we're talking properties of logarithms, properties of exponents, those types of things. Exponents, the exponents part should have been reviewed. Logarithms, we definitely expanded on. And then exponential growth, and within this exponential growth, we talked about compound interest and the different types of compound interest. And then we also talked about radioactive decay and problems dealing with those, finding the rate of decay and so on. Test 4, we looked at sequences in series, arithmetic sequences in series, binomial theorem, which hopefully you're pretty familiar with. Both of these things we've reviewed throughout the year. Solving radical equations, divisibility, and mathematical induction. So this is probably the big topic off of this one, although arithmetic sequences in series was also a big one on this test. All right, so the first basic thing I want to talk about are domain and range, and specifically in domain. What ways can domain of a function be restricted? And what I mean by that is, when do we have domain restrictions? What are some situations we should be looking out for? So first situation is when we're dividing by x. So anything in the numerator, if you have a variable in the denominator, not just x, but a variable in the denominator, we've got a domain restriction that x cannot be equal to 0. If you have a situation where, you know, x squared plus 2x plus 1, then you want to set that equal to 0 in order to find those restrictions and go from there. So in this particular case, x cannot be equal to 1. Another situation that you need to look out for is variables under a square root. And in this particular case, some values do work. Those values are when whatever's under the square root is greater than or equal to 0. So anything negative in this particular case is not going to work. If you have an instance where you've got like an x squared minus 1 under there, then we need to set that equal to 0. Figure out what those properties or what those values are for x, and go from there and solve. So that restriction, actually in this case, anything would work because of the squared value, but you get the point. So we need whatever this argument is underneath the square root to be greater than or equal to 0. Last one, and certainly there are others, but the last big one is when we're dealing with logarithms. So the logarithm of x, remember this is what exponent 10 to the what is going to be equal to x. And anytime you're going to raise something to an exponent, you're never going to get 0 because 10 to the 0 is equal to 1. You're also never going to get a negative value. And so in this case, this argument right here, this argument has to be greater than 0, strictly greater than 0. So that's some domain considerations. The range is just going to be looking at your domain restrictions, plugging those in and seeing what the value of your function is going to spit out, and then you can report your range. So the next thing that we looked at, the next kind of topic that we looked at were quadratics. And you guys should have been well versed in quadratics coming into the course, knowing how to find vertex and roots and all those other things. But what we looked at was for any given quadratic, here's the general form. We know that we can have some kind of funky quadratics, and I give a couple examples down below. We'll talk about those in a second. The definition is whatever value is here, or whatever variable is here, is going to be squared in this portion. All right, so whatever value you have here in this equation is going to be squared in this portion. So I kind of made a little bit of a funky function here. So f of the Batman symbol is equal to the Batman symbol squared minus 2 times the Batman symbol plus 3. We want to tell whether it's a quadratic. Well, do I have that form? So whatever is in this slot right here, is that squared in this particular one? For this one it is. So it is a quadratic. All right, and then in particular it's a quadratic in the Batman symbol. I'm not going to try to draw that, but hopefully you guys get the picture. Okay, so whatever I have in this slot here needs to be squared in this slot. And then if that's the case, then we have a quadratic in this thing right here. So quadratic in the Batman symbol. A little bit more traditional example, I've got the square root of x. So in order for this to be a quadratic, we're going to look at this term right here. Is this term, is x equal to square root of x squared? And in this case, we know that square root of x squared is going to be equal to x. So this would also be a quadratic. So where this really comes in is when we start solving quadratics. And so we're going to look at different ways to solve. Again, these are things that you guys should have been familiar with. The number one way to solve is factoring. It's the easiest way generally. So make sure that you're solid with that. Number two way to solve is a quadratic formula. And number three way to solve is completing the square. So all of these you should be familiar with. If you're not good with completing the square, for instance, which tends to be the toughest one, make sure that you are solid with that. There's plenty of materials and you can come in and ask questions if you need to. So what we want to do typically is I'm going to ask you to solve. You need to recognize if it's a quadratic and then use one of these strategies in order to solve whatever that the situation may call for. All right, so just to finish this up, this is a quadratic in the square root of x, and then using one of these strategies to solve it, we would say, hey, the square root of x is equal to whatever we can come up with, and then you need to solve for x and simplify. The quadratic formula is based on completing the square. So we're going to let f of x equal ax squared plus bx plus c. So we're going to start with a quadratic function. Next step is we know that roots, we can find roots when f of x equals 0. So let's go ahead and set it equal to 0. So we got ax squared plus bx plus c is equal to 0. And the next step is just going to be completing the square. So all of our work, or most of our work for this particular proof, is completing the square. We're going to move our c over. And what I'm actually going to do is factor out an a. And that's an important step. Anytime you complete the square, make sure that the coefficient on the x squared term is going to be 1. So we're going to factor out an a from this thing, which leaves us with x squared plus b over a. And we've got this term right here. We need to figure out, we need to chop that in half. So we've got b over 2a, and we're going to square that thing. So what we're left with is, I'm going to go ahead and divide by a on both sides. So this is b squared over 4a squared. So we'll have x squared plus b over a plus b squared over 4a squared equals negative c over a, and we added this to this side, so we got to add this to this side. All right, next thing is we want to go ahead and factor this. So we're going to be left with x plus b over 2a, and that's squared. I don't know why it changed colors on me, but it did, so that's fun. And that's still equal to the same thing on this side. What we want to do here is get a common denominator, and when we do that common denominator here, we would have to multiply this term on the right, negative c over a, by 4a. So we're left with negative 4ac over a. I'm sorry, over 4a squared. And now we have a common denominator, and I'm just going to flip things around a little bit. So we're going to be left with b squared minus 4ac, came from this piece here, over 4a squared. Next step, x plus b over 2a. Take the square root of both sides, square root of both sides. So that's going to end up with that's going to leave us with a plus or minus b squared minus 4ac over 4a squared. But we can actually take out, not take out, but simplify so that it's not under the square root anymore. The square root of 4a squared is simply 2a. So the last step in this is subtract our b over 2a. We're going to be left with x equals negative b over 2a plus or minus. And notice that we've got common denominators, so I'm just going to go ahead and simplify that. So that's b squared minus 4ac over 2a. And our conclusion, I ran out of room here, but our conclusion, remember we always want a conclusion. Therefore, x equals negative b plus or minus square root of b squared minus 4ac over 2a are the roots of a quadratic. So make sure you know that that proof of quadratic formula. Next thing we want to talk about with regard to quadratics, build a polynomial of least degree with roots r1 equal 5 and r2 equal negative 1, so roots of 5 and negative 1 and a y-intercept of negative 10. There are two strategies that you need to be able to do. Strategy number 1 is what we call, or I'm just going to refer to as the factor method, or the factors method. So we're going to build this quadratic based on knowing that we can write it in terms of these roots being factors. And so what we have to solve for here is the coefficient in front of this thing. So these are still the roots, but we need to basically determine how narrow or steep this thing is, or how wide this parabola is going to be. So we're going to write this. Remember, our factors are opposite the roots. So we're going to write this just like this, and then we can plug in our point. If we have an intercept, it's going to be the coordinates of that thing are going to be at 0, negative 10. Negative 10 equals our coefficient there. And we're going to plug in a 0. And you can go through and solve. So this ends up being negative 5 and 1. So we're going to divide by negative 5 and 1. Sorry, 10 over 5, or 2, is going to be our coefficient. We would want to write that as our final answer. Don't worry about expanding. We don't want to waste the time. We just want to get this thing in these terms so that we know the coefficient on this thing. The other method that you need to know is the sum and product of roots. So the sum and product of roots says that you can find the roots of any quadratic if you know the sum and the, or if you, I'm sorry, you can find the equation of a quadratic if you know the sum, or if you know the roots. So we're going to look at the sum of the roots, and that's equal to b over a. So r1 plus r2 is going to be equal to negative b over a, and r1 times r2 is going to be equal to c over a. So very simply, we can go through r1 plus r2 is 5, minus 1 is going to be equal to 4. So that's equal to negative b over a, and r1 times r2 is going to be equal to c over a. So 5 times negative 1 is going to be equal to c over a. So that's a negative 5. From this, we would be able to tell that a is equal to 1, b is equal to negative 4, and c is equal to negative 5. And you can write your function that way. Last part of this is the proof of the sum and the product of roots theorem. I'll give you a snapshot of it real fast, but I did make a video if you want to go through that video. Here's the snapshot. So essentially what we're going to do in this proof, make sure you define what your roots are, and you start off with a quadratic function. So let f of x be quadratic, and r1 and r2. And then essentially you're just going to go through and show that r1 plus r2, using the quadratic formula, that r1 plus r2 is negative b over a, and r1 times r2 is actually c over a, and then make sure you have a conclusion. So I'll let you guys check out that separate video. Where are we at here? There we go. So I'll just write on here, see the video. For the proof. Next quick topic was absolute value, and you guys have covered this before, but we looked at this in terms of the definition. And so anytime you have the definition, we call this the argument. The definition states that the absolute value of whatever the argument is equal to the positive version of the argument when x is greater than or equal to 0, and the negative version of the argument when x is less than 0. And so just as a quick example here, absolute value of x minus 3 is equal to the positive version when x minus 3 is greater than or equal to 0. So when x is greater than or equal to 3, it's equal to the opposite when x minus 3 is less than 0. And so you would solve for this, and you can condense that on your own, but you guys get the picture. Make sure that you use the definition in order to solve these absolute value functions. All right, so next thing we want to look at is matrices, and specifically Cramer's rule. So I've just got Cramer's rule here listed for you. You can look at it yourself, but essentially we're looking at, the only thing this doesn't say is this is the determinant of these matrices. So if you look at what's included here, when you're solving for x, you're going to take the solution, or the constants, and flip it with the y's. So when you're solving for x, the way that I remember this is there is no, you don't use the coefficients of x in the numerator. You're going to take the other two column coefficients and flip it. And that's how you can kind of remember that. So that's the determinant of that matrix is going to give you the numerator. The determinant of these guys here is going to give you denominator. All right, and then for the y's, you don't use the coefficients of the y's, and you don't flip for the y's. So it's just the coefficients of the x is your first column, and the constants is your second column, and it's over the same denominator. All right, so I'm not going to do an example. You guys can look back. You should have plenty of examples of those. If you don't, look up on the internet. They're pretty much everywhere. What I do want to look at is the proof of Cramer's rule. The proof of Cramer's rule can be found, where to put it? Here we go. So I look back in the notes. This, I believe, these are the notes from 9.4 or 9.3. I can't remember which one. But either way, this is a proof of Cramer's rule. So you guys do need to know this. Make sure you do. Let the following system of equations exist. So we just defined ax plus by equals e and cx plus dy equals f. So that's our system. So essentially what it revolves around is using elimination. We're going to solve for this. So I'm going to first eliminate, I'm solving for x. So I'm going to eliminate the y variable by multiplying by a scalar, and therefore eliminating these two things. So these two are going to cancel. We're left with this stuff, and essentially from there, we're just going to combine those two equations. So we've got AD times x minus BC times x. That's where this comes from, equals DE minus BF. Go through and solve for x by dividing by the coefficient of that thing. And then we can kind of turn this DE minus BF into the determinant of the appropriate matrix, and then AD minus BC into the determinant of the appropriate matrix. Always need a conclusion. All right, so therefore the x-coordinates of the solution for this system can be found using this guy. The proof of the y is the exact same thing, except up here during the elimination phase, you want to make sure that you're eliminating the x variable. So we would multiply the top by c, the bottom by negative a. That would drop the x variable off, and then go through the same exact process, combine, go through and solve for y, and you should be left with what you need for the y coordinate. So if you need to, pause the video, study that, make sure you know it. I'll give you a general overview. Start with a let statement, and you're going to start with a system like we did in the video. Number two, you're going to eliminate. So elimination method, eliminate one of the variables. Depending on what you're solving for, and solve for the other. So 3 is solve for the other variable, whichever one you didn't eliminate. Number 4, you're going to come up with an expression, and you need to convert that expression from an algebraic expression to a determinant of a matrix. And then 5, as always, need a conclusion. So that's the general overview. Not a bad proof. It's just you got to remember the general process. So we want to look at solving consistent dependent systems here. And this falls under the larger kind of realm of row operations on matrices. So we want to make sure that you review row operations and swapping and multiplying by scalars and multiplying by multiples of rows and all of that stuff. But specifically, this is the case where you have a consistent dependent system, meaning you have a solution and it's dependent. One equation is dependent upon another. And so when you graph these things, you have an infinite number of solutions. So what we need to do is, when we're dealing with, this is in 2D, this is what it looks like. But when you're dealing with this in 3 dimensions, essentially what you have are more variables than rows. or then equations, I should say. So anytime you get a system and you go through your row operations and you have more variables than you have rows, in other words, you get a row of zeros, for instance, you're going to have to introduce a parameter in order to solve that. So in this case, I kind of skipped ahead of the row operations. You guys can review that on your own, but I want to look at how we deal with this. So in this case, we know that x is equal to 2, but we need a way to go through and solve for y and z in this particular case. So what we would do is take that y value, let y equal to, or I'm sorry, let y equal t. So we introduce this parameter, and when we do that, we can go through, and if y equals t, then we know that 2y plus 3z is equal to 5, but this is not y, this is t, so we've got a 2t here plus 3z equals 5, and we can go through and solve for z in terms of t, and then our solution is going to look a little bit different. We'll talk about that in a second. So if I solve for z on here, I'm going to have 5 minus 2t over 3, and we can write our solution set. So we've got x, y, z. Just a reminder, this is how you write your solution set. X, y, z. I know my x is 2, and we're going to look at the coefficients of these things. Y does not have a constant value. It's equal to t, so it should be 0. And then z has a constant value of 5/3 if you break this up. So those are the constant solutions, and now we have to write it in terms of that parameter, write the rest of our solution using that parameter. So x is not dependent upon the parameter, so we would have a 0 there. Y is the parameter, so it's equal to 1t. And then down here we've got negative 2/3 t that we would write. And this would be our solution set to this consistent dependent system. Again, anytime you have more variables than equations, or you end up with a row of zeros, in other words, you're going to have to introduce this parameter and write your solution with regards to that parameter. All right, finding equation of a quadratic, the last portion of the matrix stuff that we're going to review. So what we end up with here is, if we've got, what we want to do is we want to use points. Use the points. So let's say 1, 2, 3, 4, 5, 6 are points. We want to use this matrix method in order to do this, in order to find the equation of a quadratic formula. So first things first, we know that the general equation is ax squared plus bx plus c. And so what we want to do is come up with a system of equations based on these points, and just plug in these x values and see what we get. So we should be able to come up with a system of equations based on this. I know that 2, the first part of my system, 2 is going to be equal to a times 1 squared, which is just a. Maybe I'll write this out for you guys. Plus b times 1 plus c. So this would just be 2 is equal to a plus b plus c. Next one is 4 is going to be equal to 9a. So a times 3 squared plus 3b plus c. Last one, 6 is going to be equal to 25a plus 5b plus c. And now we're left with a system of equations that we can use matrices to deal with. I'll show you the setup real fast just to remind you what this looks like. So our matrix is going to look like this. Here's our matrix times ABC, and that's equal to our solution matrix here. So 2 and 4 and 6, or a constant matrix, I should say. So you can go through, and again, just to remind you guys, we want to solve for this. This is the guy that we want to isolate. So I want to find the inverse. If this is A, I want to multiply by the inverse. So use your calculator. Typically, I let you guys use your calculator to find the inverse. I'm going to multiply by the inverse on this side, but if I multiply by it on this side, I better do it over here because matrix multiplication is not commutative. Make sure you understand that. Not commutative. I cannot, A times B is not equal to B times A in all cases as a general rule for matrices. So make sure that you understand that. All right, last thing we want to talk about here, I believe, are properties of exponents and properties of logarithms. These two kind of go hand in hand. You should know the forms of these things. I just kind of copied and pasted this little thing here, but basically these are all the same rules for log and natural log. So just focus on one or the other if you want. So first, looking at the product, log of A times B, you can split that into the sum of two different logs. The quotient, log of A divided by B, you can split that into the difference of two logs. This property I don't think we talked a whole lot about, but this guy right here, this is where your exponent, if you have the exponent on the argument in the logarithm, you can move it out in front. And then these two properties down here with logarithms. Only other one I really want to mention is this guy right here. So just remember that natural log has a base of e. So anytime you want to get rid of an e, those are inverse functions essentially. All right, moving on, exponential growth and decay, and specifically compound interest problems. We have three different types of interest that you're going to need to know. You're going to make sure that you know these formulas. Simple interest, compound interest, and continuously compounding interest. Different formulas for different situations. So I'm just going to talk generally about these things, and then I'll give you the formulas. For simple interest formula, we didn't deal a ton with this because this is a little bit basic, but there's your formula. The interest equals the principal invested times the rate per year, or the rate of investment, multiplied by the time in years, and that'll give you whatever you need using that formula. Next one is compound, and when I say compound, I mean compounding a finite amount of times. So a finite number of compounding periods. And this is really the difference when you look at compound interest versus continuously compounding interest. You have here, most of the time using compounding interest, you have a finite number of compounding periods. So it's going to compound annually or semi-annually or quarterly or whatever the case may be, but there are a finite number of compounding periods within a given time frame. For continuously compounding, what you're really looking at is an infinite number of compounding periods. So we've talked about essentially what you're looking at is an infinite sum when you talk about continuously compounding interest. This is usually associated with organic growth. So you're talking about, populations are generally continuously compounding. They don't only compound a few times a year. So the big difference, again, if you have a finite number of compounding periods, you're going to use this A equals the principal. So the amount of money equals the principal invested times 1 plus the rate of interest over the number of times it compounds. And again, this is not going to be infinite. Raised to the n times t, so the number of times that it compounds times t in years. When it gets to the point where it's infinitely compounding, that's when we're going to use that PERT formula. So this thing, basically, essentially, the more and more times that this thing compounds in a given time frame, it's going to approach E. We did that little investigation in class where we increased the number of compoundings or times that it compounds per year, and it approaches the value of E. And so that's why this particular thing is used when you look at infinite number of compounding periods or continuously compounding. I'm not going to talk much about this, but half-life problems were a big application of this. This is continuously compounding. If you want to think of it in terms of that, this is exponential decay. So you need to make sure that you understand half-life, how to find half-life, how to find rate, and all of those things that are associated with half-life problems.